show again the picture about the radar infrared. Can you show the picture about the radar?
Alexander class.
Alexander Freie.
Yeah. This one?
Yes. So how can they reduce the red part?
So the way I understand it, the idea is the following: that so there's a statistical model. So this is not. So this is based on real data from a mobile phone company, but then it's a statistical models about what users and how many users they would have in various places. And what you can't change is how many users there are and how many antennas you have. So the only thing that you can change is if you change the directions of the antennas, is that where you have many users, you want to have a smaller domain, and so that you put the antennas in such a way that, for example, here this little antenna captures a much too large domain, and that's why it will be overloaded. And in this case, I guess, which one was that? Somehow I'm having problems in the moment to matching things. So with a few changes and rotations and tiltings of these things.
Are kind of symmetric to each other. It's not the same thing. You make kind of mirror symmetry.
Well, they should.
Flip the center picture to get the first one. No? It is sensitive.
No, I mean, if you can overlay them, they're really, so the antennas are in the same places, but they're just rotated a bit. So the directions of the arrows, I think the lengths of the arrows indicate how much things are tilted. That's sort of just.
But what would the legend be? What the puzzle? In the puzzleation, I don't say.
Yeah. So the which domain belongs to an antenna is computed dynamically, right? So if a user is here, then he will find that the closest antenna, or the one that's responsible for him, is this one here. And so depending on how you rotate the antennas, there will be a larger or a smaller domain served by this antenna. So here, like this one, which is overloaded here, and this one here is directed a bit further up, and so it gets a smaller domain, and in the modeling it seems that then it can do it. So there's a so between these two pictures, there's quite some modeling and heavy computation. I can give you a reference. So this dissertation is online. It's a substantial work.
Other questions?
How the math chip gets faster?
So the basic idea is the following. So for this math chip, so what these engineers do, so the way I understand it, and I'm not an expert, the way I understand it, the following. I mean, all of these chips work in cycles. So they have a certain cycle time, and they are synchronized in a certain way, such that at all of the places on the chip, the cycle will start at the same time. And what people in Bonn noticed and then used is the following: that first, even if you synchronize things, you will never synchronize it completely. And secondly, actually, it doesn't even make sense to synchronize it completely. It's important that everything on the chip goes in the same cycle, but it's not important that the cycle starts at the same time everywhere on the chip. So what they did is that they would take some components which would start each cycle a bit earlier, and there's other components that start each cycle a bit later. And so if you build that in, that some things are earlier and some things are later, then you find that there's cycles which say there's travel time from here to here, travel time from here to here, travel time from here to here. That if you make this then this a bit later, and this a bit later, and then this one you start the next cycle, then suddenly you can fit things in that otherwise you couldn't. So in the end, this reduces to directed cycle and flow problems from combinatorial optimization. And the mathematics that's used at this part, I mean, they developed this here, but it's really based on standard things from combinatorial optimization that we understand at least since the 1960s. But here this was used for the first time, then packaged in a software package called CycleOpt, which is part of a software suite called One Tools, which IBM, who made this chip, and various other producers around the world use to design and optimize their chips.
I'm wondering who the name of the person who wrote this book with this long design, who's the name of the book?
The name is Robert Record. I think with the E at the end. So the, yeah.
He's a French mathematician?
No, he's from Wales. So British and apparently a doctor and mathematician. So he wrote several mathematics books, but he was also the apparently personal doctor to one or two British queens and kings. And in the end, I think he died in jail after amassing too much debt right after this book was published. So there's a rather dramatic life story behind this. So if you look for him on Wikipedia or for the equality sign of Wikipedia, you will find it.
Have you tried to speak with the Russian fellow or
no, but and I don't know who that was. But actually, I did talk to the people who did the statistical analysis and the people who produced this graph. And so there's a Russian ex-physicist from Moscow, Sergei Shpilkin, who has for years been involved in election analysis. And he has done this together with two colleagues, one in London and one in Amsterdam. They have a paper on the archive about analysis of this 4th of December 2011 election and subsequent presidential election. And so I talked to them over email, and they explained to me also about some of these peaks that are come from analysis. When they produced these graphs, apparently they were shared over Facebook and the internet, and so there were various demonstrations where these things were held up. So we don't know exactly who this was who held this poster, but we do know where the poster comes from. And so also this mistake with the poster, this peak at 50% really, somehow they hadn't noticed that when they first made the graph, though they knew about the effect. And so this spread like a virus over the internet, and so there was no way to recall that.
questions? Okay, so you might have a tea and coffee outside, and then things wonderful job